Hello everyone, my name is Delphine Demange and I'm going to present our work about the formal verification of intermittent computing with peripherals. Intermittent computing systems are tiny autonomous systems such as wearable devices, RFID tags, or smart cards. They have no battery. Instead, they capture and store energy from an external source like solar, thermal, or wind energy. These systems are subject to frequent power failures when the supply voltage is insufficient. So to deal with power failures and ensure progress, a checkpointing mechanism is used. Before power completely runs out, the state of the system is saved to a non-volatile memory. After an unpredictable period of time, the system can boot again, at which point the previous state is restored. Checkpointing can sometimes fail, so we must make sure that we restore only consistent states. Of course, these systems are not made of just a microcontroller. They include peripheral devices, here in the blue box. Research-wise, the last decade has been fruitful, and a number of work tackled the problem of intermittent computing with peripherals. And two main challenges emerged from the literature. First, peripheral state is both volatile and opaque to the microcontroller. Second, peripherals have an observable impact on the environment, and timing constraints can raise problems such as atomicity or timeliness of peripheral accesses. And many frameworks propose some solution to deal with these two challenges. In this work, the question we ask ourselves is, what is the rationale and general principles behind those frameworks? So in this work, we formally capture the essence of transiently powered systems with peripherals, in a way that we want to be completely independent from a particular implementation. First, we propose a specification for intermittent computing with peripherals. So we provide an abstract programming model that developers can rely on. A key ingredient of the model is to be able to express meaningful sections of interactions with devices. This is what we call power continuous sections. Second, we propose a formal model of a checkpointing scheme based on interrupts that detect voltage drops. That's the PLF system for power loss and failures. And we identify two basic components: the logging of peripheral operation, so the log component here in green, and an interface for persistent checkpointing, the checkpoint component in light blue. And finally, we prove that our checkpointing model is semantically correct. That is, it implements the abstract programming model. And the proof of such a result can be tricky because of many corner cases, so we mechanized our proof in the Proof Assistant. Okay, let's start with the specification. That is, what programming model should we have in mind? The system is made of two components, the MCU and peripheral devices. Checkpointing volatile state from the MCU is fairly standard, so to describe it, we just assume a set of states, abstracting CPU register, RAM, etc. Now regarding devices, to handle challenge number one, we should distinguish the physical devices from the interface they expose to the program. So indeed, we model devices as a set of states, abstracting physical devices, plus a set of device operations. Take for instance a radio transceiver. You would have idle state, calibration state, receiving, transmitting states, and the expected operation. Now, to describe the evolution of physical devices, we assume a transition relation that reflects how operation makes the state evolve. This roughly corresponds to the device state diagram that you can find in the user manuals. This abstract model of devices makes no assumption whatsoever about the actual behavior of devices. And while it is very simple, it does account for multiple devices. You just have to combine the states and the transition relations. So We now describe how the whole system behaves, and we do it with a simple two-mode state machine. User mode executes standard application code, leaving devices untouched. In contrast, driver mode is used when interacting with devices, effectively changing their state according to the transition relation dev. Note that this machine is highly non-deterministic and accounts for preemptive or concurrent systems. And as you can see, there is no power loss in this specification. Indeed, the system should behave as if it were continuously powered. But still, driver mode is used to handle the atomicity and timeliness of devices' accesses. Depending on the application and devices, we specify when mode switching must be done. Driver mode, in some sense, delineates what we call power continuous sections of code. Sequences of instruction in a power continuous section behave atomically with respect to power loss. And this guarantees that these sequences of interaction with devices are meaningful. Now, challenge 2 is also saying that what matters is the impact of devices on their environment. So what we do is we define the observable behavior of the whole system as traces of device operation emitted at runtime. And by construction, these traces comply to power continuous sections. So now that we have a specification, let's see how we model the interrupt-based checkpointing scheme. So now the system, PLF, is subject to power failures and must be checkpointed. The first brick we need is a mechanism to log interaction with devices. And this is related again to challenge 1. Remember, peripheral state is volatile, so it must be kept track of. And as device state is opaque to the MCU, we need to go through the device API. So we assume a set, log T, of abstract summaries of device states. A summary can be extended with a function that we call log that adds an extra operation to the current summary. And we further assume to have a function, restore, that given a summary is able to recreate the corresponding device states. This is an abstract, generic specification, but it captures existing framework like CTAR or RESTOP. The only requirement about it is a commutation diagram between the function log and restore. And this is a basic consistency condition that we have identified for the operation logging to be correct. Now, the second key ingredient is an interface with a non-volatile storage where to store checkpointing information. Checkpoint.t is an abstract set representing snapshots of the state of the system, so morally the MCU and the operation log. And to ensure progress, checkpointing usually relies on a double buffering mechanism. So morally, a snapshot hence comprises two images of the system. So we assume two functions, cur and last, that respectively access to the current and the last valid image of the system. So here again, our model is very generic, in particular in log T. So we further specify it using functions and a simple equational theory. So the current image can be dynamically updated using the two save functions, save MCU and save log. So either we update the current MCU image or the current operation log. And finally, we need a way to commit or abort the current image. So the set function commits the current image by making it become the last valid image. In contrast, the reset function aborts the current image by resetting it to the last valid one. We now have all the ingredients to present the checkpointing scheme. We formalize it using another state machine that refined the spec machine. We extend it with the non-volatile checkpointing storage and also a volatile log that is used only in driver mode. We also use the checkpoint and log function to keep the components up to date. So for instance, switching from driver to user mode is when the volatile log must be saved to the current non-volatile image. Now, in order to account for the various power loss scenarios, we introduce two extra states to the machine. State power is when a voltage drop is detected and all the volatile state is discarded. And state off is when the system ran out of power completely. Only from that state, the system will reboot, restoring the system in a consistent state. Power loss scenario introduce further non-determinism to the state machine. First, a voltage drop could occur at any point in time. It can be in user or driver mode. Second, the checkpointing can fail to be committed before power runs out. And finally, it could be that power outage occurs immediately without voltage drop is even detected by the hardware. So now, how should we define the observable behavior of this checkpointed system? Well, in fact, it appears that just emitting a trace of device operation is not enough, and we will see why in a minute. This is in fact related to the statement of semantic correctness that we present now. Informally, what we want to prove is behavior of the whole checkpointed system should adhere to the specification. So, in other words, we have to relate a transiently powered system, PLF, with a continuously powered system, spec. And in PLF, due to reboots and restarts of power continuous sections, some device operations are replayed. This is unavoidable, and here the functional correctness of the system relies on a idempotent environment. Now, in order to express a meaningful mapping between the two executions, we must distinguish fail attempt from repeated progress. So to do so, we instrument the trace of the PLF machines with extra observable events. The log events indicate whether a power continuous section has completed or was aborted. And the checkpoint event indicate whether the checkpointing failed or was successfully committed to non-volatile memory. So in fact, the emitted trace of the PLF machine would look like this. So really, instrumented trace allows us to distinguish the various scenarios. In the example, first, the power continuous section was completed, but checkpointing failed. Then the power continuous section aborted, but the checkpoint, while unchanged, was indeed committed. And finally, the power continuous section completed, and the checkpoint was successfully committed. So here, only the last portion of the trace should be considered as progress, and the rest are failed attempts. So to relate traces of PLF to traces of the spec machine, we design a subtrace relation that retains only the relevant part from the PLF traces. And once we have this subtrace relation, we can prove the following correctness theorem. For any trace of the PLF machine, we can find a subtrace, T, a subtrace of the initial trace, that can be emitted by the spec machine. And this theorem means essentially that peripheral operations are preserved and power continuous sections are complied with. Okay, let's briefly recap. With this work, we wanted to step back from the implementations and figure out the underlying principles behind checkpointing from intermittent systems with peripherals. This comprises an abstract programming model where no power loss occurs, but where one can specify with power continuous sections how peripherals should be accessed in a timely manner. With our formal model of interrupt-based checkpointing, we identify two key components as well as a handful of fundamental properties they ought to satisfy. And our semantic correctness theorems boils down to a clear and simple trace inclusion property modulo the subtrace relation, which abstracts away repeated failed attempts to interact with peripheral devices. Now, in this work, we have made the simplifying assumption that NVM was solely used to store checkpointing information. We are currently extending our models to include NVM application state. And this would allow to capture more recent frameworks like Samoyed. So for more information about our work, please check out our webpage where the Cork formalization is also available. Thanks for watching.